All right, so 3-2, we introduced two theorems that are kind of, they're really intuitive when you hear them. Rolle's theorem is the first one, named after, of course, the mathematician who gave these conditions. It's right there in the middle of page 168. It says theorem 3.3 is Rolle's theorem. Let f be continuous on the closed interval ab and differentiable on the open interval ab. If f of a equals f of b, then there's at least one number c such that f derivative of c equals 0. So look at the picture there. What they're saying is if your y value on this graph is the same at the beginning and the end, which you can see from this parabola that it is. So you plug in a, you get a y value of d. You plug in b, you get a y value of d. They're the same. Then somewhere in between there, you're going to have a 0 slope. Or it's going to be a horizontal. It's going to be like a y equals d, but even then, your slope's going to be 0, even if the whole line is 0. Because no matter how many times you turn in between it, if you get back to where you started from, you have to have a turn. It just makes sense. And they even show it on this where it sharply turns as well, that there's still going to be a 0 there. And so somewhere, as long as it's a closed interval, so key things here. In order to even have Rolle's theorem, you have to have a continuous function. So if it's not continuous, you couldn't say that. Because if it's not continuous, it could just break and jump and get back there. So it has to be continuous. It has to be a closed interval. So we're talking about that it includes the endpoints. And it has to be differentiable. So you have to be able to take the derivative on that interval as well. If for some reason you can't take the derivative, then it's not. And so they could say use Rolle's theorem and give you something. And if all of these things don't meet, then you would just say, I can't, it doesn't meet Rolle's theorem. So it has to be continuous, it has to be closed, differentiable, and your beginning and ending points have to be the same y value. If all of those meet, then you can then take the derivative and say, here, see, here's my derivative at 0, because it has to happen.
So when would it not be
So differentiable, it's typically also not continuous if it's not differentiable in that interval, typically. There may be, well, even continuous, I'm trying to think. Most of the time you'll see that in the continuity, that it's not going to be differentiable there either. So find the two x-intercepts of f of x equals x squared minus 3x plus 2 and show that f derivative of x equals 0 at some point in between the two intercepts. Well, they use the intercepts because the x-intercept is where y is 0. So that it's beginning and ending point of the same y value. So we're just going to find the intercepts. We're going to do that by setting this equal to 0. They want the x-intercepts. That's where y is 0. We're going to set it equal to 0. So we'll get x minus 2x minus 1. So at x equals 2, f of 2 is going to be 0. And at x equals 1, f of 1 is going to be equal to 0. And so they want us to prove that Rolle's theorem applies in that interval. They want us to use that particular interval from 1 to 2. So this is a parabola. This is a continuous function all over. It's definitely continuous from 1 to 2. It's differentiable. Again, it's a continuous function here. It's differentiable on that interval. And it has the same starting and ending value because we just chose it. So we have the same starting and ending value. So to prove that, we're going to take the first derivative, set it equal to 0, and find that value, and then show that that value is in this interval. So we're going to do first derivative, which is simple first derivative here, 2x minus 3, right? We're going to take that first derivative, and we're going to set it equal to 0. So that's going to be 3/2. And then we're going to say, does 3/2 fall in this interval? Yes, it does. So this proves Rolle's theorem. So Rolle's theorem applies here. We've proven that it is continuous. We've checked off all the boxes. Starting and ending value are the same. And then where we have the 0 falls within our interval. And if you look at the graph itself, you can see you have a parabola. It dipped below the line here. So starting here value is 1, 0, ending value is 2, 0. We have a turn right here at 1.5, which gave us a critical number of 0. They give us another function. Find all the values of c in the interval negative 2, 2 such that f derivative of c equals 0. So before we even start using Rolle's theorem, we have to then say, are my endpoints the same? Because if they're not the same, you can't prove it, right? And so if in this situation they gave us the endpoints, we're going to the very first step here is to plug them in and prove that they're going to equal the same thing. So negative 2 to the 4th, that's 16, minus negative 2 squared is 4, times 2 is 8. So that's going to equal 8. Then we're going to do the same thing for the other endpoint, f of 2. 2 to the 4th minus 2 squared. That's again going to be 16 minus 8 equals 8. So we checked off the first box. Beginning and ending point have the same y value. And so now we're going to take the derivative. So derivative of x, it's going to be 4x cubed. I went backwards. 4x cubed minus 4x. So we want to set this guy equal to 0. So it is differentiable on that interval, by the way. We're going to set this equal to 0 and solve it. And so we have x equals 0, x equals 1, and x equals negative 1. And actually all three of these are on the interval. Now, there will be times when you could have a critical value that fell out of that interval. As long as one of them fell in it, you're proving Rolle's theorem. In this case, all three of them do. So here we can see that from negative 2 to positive 2 interval, actually all three of these fall in that. So yes, Rolle's theorem applies here. And you can see what the graph actually looks like. They went from negative 2, which gave us an 8, positive 2, which gave us an 8, and we actually have 3 0 slopes in that short interval. Now, had they given us, let's say they had given us some other one that gave us the same value, like right here, we look like it maybe negative 1.5 to positive 1.5 might be the same thing, is fine. Or you can see if they had given us an interval like from here to here, they're both at 0. Even though doing this function, we would have found 3 critical numbers, the only one that would have fallen in this interval would have been positive 1. That's okay. As long as one of those values falls in the interval, Rolle's theorem applies. So the mean value theorem, they actually use Rolle's theorem to prove this, but what the mean value theorem says that if f is continuous on the closed interval a, b, and differentiable on the interval a to b, then there exists a number c in a, b such that, and you see this little formula looks vaguely familiar. They're basically saying, yeah, this is the average rate of change. This represents instantaneous rate of change, right? So if you have a continuous closed interval and you have the average rate of change, then somewhere on that interval, you're going to have the instantaneous match the average. It makes sense? So if you were to do it like, let's say losing weight. So let's say you're losing weight, and they're tracking your weight every day. And you go from 150 pounds to 145 pounds, which means your average weight over that period of time was 147.5 pounds, right? What this is saying is it's continuous. Weight loss doesn't jump. Obviously, it's a continuous. Somewhere in that period of time that you were watching, you would have been exactly that median weight because it's a continuous function. The example that they use is speed. If your average speed driving from here to Columbia is 50 miles an hour, then somewhere in that range, now, so you started at 0, you drove out of your neighborhood at 25, you drove on Ashley Phosphate at 45, you drove on the interstate at 65, 70, depending on where you were, right? In Columbia, you drove 45 and 20. They're saying if your average speed was 50, somewhere in that interim, you drove exactly 50 miles an hour. Your average speed matched your instantaneous at some point along that line. Right. Given this function 5 minus 4 over x, find all the values of c in the interval 1, 4, such that the average, such that f of c equals that average. All right? So a lot of times they'll say just prove the mean value theorem here exists. And so you're going to use your endpoints, you're going to plug them in like this first. So we plug in f of 4, so if we plug in 4, we have 4 over 4 here. So we have 5 minus 4 over 4, which is just 5 minus 1, which is 4. We plug in a 1, we get 5 minus 4 over 1, which is just 1. And so our average is going to be f of 4 minus f of 1 over 4 minus 1. It's just 1. So now we're going to take the derivative of this guy. So the derivative then, and I would rewrite him 5 minus, instead of 4 over x, I would say 4x to the negative 1. All right. My 5 zeros out. This is negative 1 times negative 4, which is 4. X to the negative 2, or we would say 4 over x squared. That is my derivative. We no longer, for mean value, we don't want to set that equal to 0. We don't want to know a critical number. We want to know where it equals our average. And so we're going to set that equal to our average. 4 over x squared equals 1. And you can multiply it over. So 4 equals x squared. X is going to equal either positive 2 or negative 2. Now, keep in mind, we want it on the interval of 1, 4. So the only one that actually meets this criteria is where c equals 2, or where x equals 2. All right, this word problem says 2 stationary patrol cars equipped with radar are 5 miles apart on a highway as shown in the figure. As the truck passes the first patrol car, its speed is clocked at 55 miles an hour. 4 minutes later, when the truck passes the second patrol car, it's clocked at 50 miles an hour. Prove that the truck must have exceeded the speed limit of 55 miles an hour at some time during the 4 minutes. All right, so we have to do it in miles per hour. So the first thing you want to talk about is that time, 4 minutes in hours. So the time in hours is going to be 4 out of 60 minutes, which is 1/15 of an hour, because we're talking about miles per hour. Much easier to do that than to try to do miles per minute here. So 1/15 of an hour. The starting point, so we would say the starting point here would be 0 then, and the ending point would be 1/15, because we're talking about in hours. So at 0 hours, he was at the 55 miles an hour, and then he was at 50 miles an hour, right? And so we would say if our x's, so to speak, were 1/15 and 0, right? Then our plug-in value, at 0, he was going how much per hour? Well, at the first one, he was going 55 miles an hour. And at the second one, he was going 50 miles an hour. So that's what we would do if we plugged it into what we're talking about, what his x and y value was. So if we looked here, we would say, well, we would take 50 miles an hour minus 55 miles an hour, and we would take 1/15 minus 0. Now, I will say that they did an average velocity, so we're not going to take negatives into count here, because he slowed down, obviously. So we would say just 5/115, because we're not talking about positives and negatives when we're talking about just how fast he's going. that's going to be 75. So what we're saying is his average speed in that short period of time was 75 miles an hour. So somewhere in that he sped.